Hi, hello everyone. First of all, thanks for being here in my YouTube channel. Let's talk about synchronous generator or AC generator or alternator. Generator which converts mechanical to electrical. Everybody knows, right? Synchronous generator rotates at synchronous speed or constant speed is called as synchronous generator. Let's see how. There is a magnetic field is present, right? North pole to south pole. I'll be coupled with one turbine over here. So when turbine start rotating, what happens? This magnetic field also rotates, right? In this manner, right? So when magnetic field rotates here, conductors are present over here. So when conductor cuts this rotating magnetic field, what happens? Induces EMF, right? Here there is a three-phase output. This three-phase output is directly proportional to this synchronous speed. I mean rotation of this rotating magnetic field is called as synchronous generator, right? So another name is AC generator, generates alternating current, and another name is alternator. Alternator produces alternating quantities like alternating voltage and alternating current, right? Let's see working principle and construction of synchronous generator. Before getting into the topic, we'll see the application where exactly we are using synchronous generator for better understanding, right? In general, if you visit any power plants like hydel, thermal, nuclear, gas power plants, wherever you go, there we are using a synchronous generator for power production. I have taken one photo. Here there is a wind turbine is present, windmill. So it is coupled with a gearbox. What is the use of gearbox in your bike? To increase the speed rate. Here also same to increase the speed. So it is coupled with a alternator or synchronous generator shaft. So here there is a magnetic field is present, right? When turbine start rotating, this magnetic field also rotates, right? Because it is coupled with a shaft. This rotor is coupled with a shaft. So what happens? Induces EMF. This EMF in the thermal, hydel, wind and nuclear power plants 11 kilovolts. Okay, this is the induced voltage, right? Here there is another one example. In car also we are using alternator. See here in the front of the car. So there is an engine present. Engine shaft is coupled with alternator. So engine gives mechanical input for the alternator. So alternator, what happens? It converts mechanical to electrical. So whatever the electrical output is stored in the battery. So battery gives supply for lightning as well as other electrical usage, right? Some more example for understanding. If you visit any hydel power plant, we can find this type of arrangement. Here there is a turbine present, water inlet over here. When water hits the turbine, what happens? Turbine start rotating. This turbine shaft is coupled with a synchronous generator, this part. So when generator start rotates, so induces EMF. Output we will get it. Here there is a hybrid car. Widely we are concentrating this type of cars. There is an internal combustion engine. Mechanical output it will give to the alternator. So alternator which converts mechanical to electrical. It gives electrical motor one input and another one is for battery. So battery stores the energy and it gives lightning as well as other electrical usage for the car. Okay, this is our part, alternator part. As you can see the picture I have taken from the power plant. This one is a rotor, rotating part of the machine, and this one is a stator, stationary part of the machine. See here, only 2 members are standing. So 100 members they can stand, and it covers around 60-40 side. These type of stator and rotor, these type of big stator and rotor we can find in the thermal power plant and the nuclear power plant. So these type of turbines we can find in hydel power plant. It is coupled with Pelton wheels. Okay. So this one is a rotor, this one is a stator. See how they are constructing synchronous generator. Let's move on to the syllabus. Operating principle of synchronous generator. In general, all generators works on the principle of Faraday's laws of electromagnetic induction. Right? When conductor cuts the magnetic field, EMF is induced, or rate of change of flux linkage is directly proportional to induced EMF. See here, there is a magnetic field is present, that is constant from north pole to south pole, just you assume. Okay, conductor is rotating, right? So when conductor cuts the magnetic field, what happens? Induces EMF, right? That is output, right? So similarly in the synchronous generator, that is reverse. Conductor is stationary, magnetic field is rotating. So in this conductor cuts this magnetic field, what happens? Induces EMF, that is in three phase output. That is the induced voltage or induced current. See, I have given one example over here. There is a magnetic field is rotating over here. These three conductors are placed 120 degree apart each other like this. Okay. This is a R conductor. induces voltage VR, this one Vy, and then Vb. So when magnetic field is present over here like this, what happens? So this conductor cuts this magnetic field, but conductors are stationary, keep it in your mind. So induces EMF in this conductor like this, and then like this, and then like this, right? Sine wave, this one, right? So this one is 0 degree, 60 degree, 120 degree, this one is 180 degree, right? So if you want VR is equal to Vm sin omega t, and Vy is equal to Vm sin omega t. All conductors are 120 degree apart each other, keep it in your mind, okay? Minus 120, just I considered clockwise direction. Vb is equal to Vm sin omega t plus 120, right? Or minus 240 also, okay? 120. This is the principle. So according to Faraday's laws of electromagnetic induction, keep it in your mind. See the diagram, how exactly flux will distribute inside the synchronous generator. I'll be just connecting one turbine over here, just to assume, okay? And if suppose turbine start rotates, this rotor will also rotates, right? So flux will distribute like this. These are the pink lines will be there, right? That pink lines are just to assume flux lines, okay? See here, there is a conductor present in the magnetic field. When conductor cuts this magnetic field, rotating magnetic field, what happens? Induces EMF in the three set of conductor, that is three phase output. Okay. So likewise, principle will be working in the synchronous generator. When conductor cuts the magnetic field, EMF is induced. When rate of change of flux linkage occurs, I mean, if suppose flux linked with the armature conductor, what happens? Induces EMF, right? Let's see very important topic, constructional features of synchronous generator. As you can see the diagram over here, there is a conductor present, just to assume, okay, in these slots. Okay. So here there is a magnet is rotating, right? So magnetic field is rotating like this. So when we give supply, DC supply to the this electromagnet, what happens? It will excite. So it will distribute flux like this, right? So distribute flux like this as well as rotates in the synchronous speed, because mechanical input is connected with here, right? So turbine is connected here. So when start rotating, the magnetic field also rotates like this. So these conductors, stationary conductor cuts this magnetic field, what happens? Induces EMF. According to Faraday's laws of electromagnetic induction, when conductor cuts the magnetic field, EMF is induced, right? So I'll redraw this diagram, construction part. One circle, okay? Diagram over, will name the parts, but the diagram must be complete proper circle, okay, not like a egg shape. Okay, this one is yoke, and stator slots, stator armature conductor, and this is the stator part, okay. And next there is a rotor part, so field winding, and this one is a pole or pole core. This one is pole shoe, and this one slip rings are brushes for giving power supply to the synchronous generator rotor field excitation. Okay, just for excitation purpose we are giving this one. Okay, don't confuse this plus minus for only excitation of field winding purpose. Okay, and this one is output R YB, or this one YB, output. Okay, this one is base. We'll explain now. There is a two part of the synchronous machine. One is stator part, another one is rotor part. This part is rotor. First one is stator, stationary part of the machine. Okay, so yoke will be present, and stator stator armature conductor. Okay, and also cooling purpose we are having some cooling holes. I mean ventilating duct. Next there is a rotor, rotating part of the machine, right? Rotor. In that we have a pole core, pole shoe, and field winding, and for excitation brushes and DC supply. Okay, and shaft will be there, right? So first one, stator is the stationary part of the machine. What is the purpose of yoke? Yoke is the outer cover of the machine, and also it avoids entering of dust particles, moisture contains inside the machine, and also it holds this stator teeth or stator slats. Okay. Next there is the stator slats to holding the stator armature conductor, and it is made up of cast iron or silicon steel. Keep it in your mind. And next there is a armature conductor. When conductor cuts this magnetic field, what happens? Induces EMF. So armature conductor made up of copper, right? Work has to be done in the armature conductor. So induces a three-phase voltage. These are three set of conductors. It connected here or some number of turns will be there. Next there is a rotor. Rotor is a rotating part of the machine. Keep it in your mind. Here we are having pole core. This is the pole core. Okay. Pole core is for to holding the field winding, and it is made up of cast iron or silicon steel. Cast iron is for low rating machine, silicon steel is for high rating machine. Next there is a pole shoe to enlarge the this area as well as to enlarge the flux like this. Okay, like this. So and it is made up of cast iron or silicon steel. Next there is a brushes here for giving the supply to the field winding for excitation purpose. Okay. Next there is a field winding. Field winding is for to inducing the flux inside the machine, because flux should rotate here and here, right? Next is the shaft to holding the this overall rotor. Here we are connecting. Just to assume here there is a shaft is coupled with one turbine, right? When turbine start rotating, what happens? This there is a we are giving power supply to the brushes, so it excites. Field winding will excite, so it rotates like this. Okay, inside the synchronous generator. So what happens when conductor cuts this magnetic field? Induces EMF in three phase. Okay, you can draw like this diagram also. This one is a 4-pole synchronous generator. This one is a 10-pole synchronous generator. But direction must be like this. Okay, so if suppose direction is opposite, definitely we can consider as a synchronous motor. Okay, once again revise parts of synchronous generator. Yoke is the outer cover of the machine, and also it avoids entering of dust particles, moisture contents inside the machine. Mechanical support to the stator slats, and stator slats holding the stator armature conductor. And also in the yoke there is a ventilating arrangement will be there, holes will be there for cooling purpose. Next there is a armature conductor. When armature conductor cuts the rotating magnetic field, induces EMF in three phases like this. Okay, and next there is a rotor, rotating part of the machine. Here there is a magnetic field is present. So electromagnet we have to give excitation supply. Okay, just here they have given, right, just this supply needed for excitation purpose. So pole core to holding the field winding, pole shoe enlarging the this area as well as flux distribution purpose, enlarging the flux also, and also here there is a field winding to produce a magnetic field. Okay, and next there is a base for holding the overall machine. Okay, once again, generator which converts mechanical to electrical, motor which converts electrical to mechanical. Synchronous speed, so that is a rotating magnetic field speed. So that is Ns equal to 120 by P, because conductors are placed 120 degree apart each other, right? So operating principle is electromagnetic induction. So these are the types of slots: wide open type slots, semi-closed slots, closed type slots. Here like this. Okay. So this is in the yoke, and then this one is a stator slots. These type of slots are available. Okay. We'll differentiate types of rotor in the synchronous generator. One is salient pole or projected pole type, already over this diagram. Another one is smooth cylindrical or non-salient pole type rotor. This one is a diagram for salient pole. This one is non-salient pole diagram. Don't feel a difficulty. This diagram is very easy. Just to draw like this. Okay. See, poles are projected out from the surface. So here, poles are projected out from the surface. Here, unslatted portion is called as a poles. Keep it in your mind. Air gap is non-uniform. See here, air gap is non-uniform because uneven surface, right? But here, air gap is even surface, right? Complete. And diameter is high and axial length is small. So this diameter is high, okay? And here, this diameter also high. But axial length is small, here to here, okay? Next, here, diameter is very small, okay? But axial length is very uh, high. Mechanically weak silent pole, mechanically strong non-silent pole. Preferred for low speed alternator, preferred for high speed alternator. For example, Pelton wheel rotates only 500 maximum speed RPM, right? So they are using this type of turbines and IC engine also. But prime movers like steam turbines or electric motors. Steam turbines in the thermal power plant, nuclear power plant, the turbine rotation is around 500 to 3000 RPM. They are using this smooth cylindrical type rotors. Same size, rating of smaller than the cylindrical type. So this one is uh, smaller than cylindrical type, but this one is higher than silent pole type. Okay, for same size. Okay, and separate damper winding is provided. Damper winding is for starting purpose. Okay, separate damper winding is not required for non-silent pole or rotor.